We have talked quite a bit about the metric system and writing numbers in scientific notation, but the third part of this package deal is a certain little concept that we call significant figures. So what are these figures? And when are they actually significant? When someone says, I drove 300 miles just to be here today, but they stand corrected by a friend who knows the exact distance of the trip, it goes to show that a discrepancy of 12 miles may not mean much if the drive was around 300 miles in total. Or when someone says, I've written about 1,000 articles for the newspaper, you are left to wonder, how can they have kept track of their near 1,000 articles? Is it really 1,000 or is it actually 932? What if it's more? The accuracy of these numbers determines how many of the digits in the number are significant. So when your sister comes home and brags about the high-end dress that she bought at a bargain price of $57.82, she's proud of all $57 and each of the 82 cents that she spent, and she doesn't see a point in rounding up the cost to $60. When we do various calculations, our calculators will give us extremely large or incredibly small values. The problem is, we can't always be as precise as the calculator says. For example, if you calculated the number of seconds in a day, you would find that there are 86,400 seconds in every 24-hour period. But you could also round this number and say that there are about 86,000 seconds, or almost 90,000 seconds, and not lose a lot of the information there. The magnitude of that number is still understood. So when someone asks you, how old are you? The typical response is to tell them your age in years, if you're comfortable divulging that information. But if they ask you for your age in seconds, what difference would 1,000 seconds make? By the time I finish this sentence, another 5 seconds has added on to your age. And now another 2. And another. And another. So it makes you think, does that amount of precision really matter? Well, sometimes it makes a world of difference. So let's work through some examples where we'll determine how many significant figures are in each of these numbers. Here we have the number 15,000. The number is greater than 10, so the exponent will be a positive number. We take that imaginary decimal point and move it to the left 4 times to create a number between 1 and 10, as per the first step of writing a number in scientific notation. We don't need those 3 zeros anymore, so we get rid of them. After including the power of 10, which is 10 to the power of 4 here, 4 because we moved the decimal 4 times, and positive because we moved it to the left, we can now count how many digits are left over in the coefficient of our expression in that underlined region. There are 2 digits, so this number has 2 significant figures. This next number, 0.0043, is smaller than 1, so its exponent will have to be a negative number to represent the tiny value. Take that decimal point and move it over to the right 3 times, so that it will sit behind the first non-zero digit to create a number between 1 and 10. We again remove the zeros that we don't need. And after counting the number of digits present, we can now say that this number, written in scientific notation, also has 2 significant figures. So we can see that anytime any of these digits show up in a number, no matter where they are placed, they will always be significant. But what about the 0? We noticed in the last 2 examples that we dropped the zeros from the expression. But do we always do this? Let's find out. Here we have the number 0.0050. Again, it's very small, less than 1 in its value, so that exponent will again be negative when we write it in scientific notation. Again, we move the decimal to the right 3 times so we can create a number between 1 and 10. But here comes the funky part. Which zeros do we remove? Do we get rid of all of them or just some? Well, we have to get rid of the zeros that are just the placeholders for the decimal, but the 0 that comes after the first significant digit that comes after the decimal must remain in our number. So when we write 0.0050 in scientific notation, we get 5.0 times 10 to the power of negative 3, which is a number that has 2 significant figures. To summarize, we can use these rules to determine how many of the digits in a given number are considered significant. Any number that is not a 0, no matter where it appears, is always significant. Any zeros sandwiched between these non-zero numbers, which are significant in and of themselves, are significant too. Any 0 that trails after the last non-zero digit after a decimal point is also significant. The zeros that appear after the decimal point but are found before the first non-zero digit are not significant. They're just placeholders, so they don't really carry much weight, which is why we were able to cancel them out and drop them from the expressions previously. Lastly, the zeros that appear before a decimal point are also just placeholders, included for cosmetic purpose. So these too are not significant, which makes this number here a number with 7 significant figures.